All right, good morning, everybody. My name is Olivier Pierron, and I'm the faculty coordinator for this Mechanics of Materials concentration area. So because this is supposed to be a short presentation, let me go to the point. To satisfy this concentration area, you have to take two required courses, and that's machine design, which is your design elective, and mechanical behavior of materials, ME 4214, which will also satisfy your ME elective requirement. Then you have to choose any 3 electives from a list of 12 courses. And this is the list of the electives. Out of these 12 courses, 6 of them are non-ME courses, and only 2 of them have a prereq that would require you to take additional courses. Although one of them, Structural Analysis 2, has for prereq Structural Analysis 1, which is part of the list. And also note that one of the courses is ME 4699, Undergraduate Research, so long as the topic is related to mechanics of materials. So we try to keep that list of electives as large as possible, so you have a lot of flexibility within this concentration area. And like I said, you can choose any 3 electives you want, or if you want, you can follow our advice. Let's say that you have a specific interest in design of materials, or biomaterials, or large-scale structures, theoretical mechanics. We would recommend that you take these specific electives. Or let's say that you're interested in graduate studies, but you're not sure if this is for you. We recommend that you take undergraduate research, so you get some research experience beforehand. Speaking of which, let me give you a very brief overview of what we do in the Mechanics of Materials research group. And we basically do a lot of research on topics related to the deformation, creep, fatigue, fracture, and durability of a broad range of engineering materials, heterogeneous engineering materials. And so we specifically focus on experiments and modeling of the effects of the structure of the materials on the mechanical properties. And we do that across a wide range of scales, from the nanoscale to the microscale. We focus a lot on nonlinear and time-dependent material behavior, plasticity, fatigue and fracture of materials, and also foundations of system-based design of materials. What that means is that there is a wide range of research opportunities in this area, as highlighted with a few examples. Examples of molecular dynamics simulations, fatigue properties of small-scale materials, micron-scale devices, thin films, or fatigue properties of larger-scale components. If graduate school is not for you and you're more interested in going directly to the industry, I think with a background in mechanics of materials, the job opportunities are plentiful. And this is a number I actually like to give when I teach fracture mechanics or fatigue on the first day of class, and that's the approximate cost of fracture in a modern country like the US. And that's about 3% of the GDP. So what that means for the US, it's about $500 billion every year worth of money due to fracture, B with a billion with a B. And that cost includes repair of fractured components, but also prevention of fracture and research towards better prevention. So what that means is, with a background in mechanics of materials, specifically fatigue and fracture, there will be a lot of job opportunities for you as mechanical engineers in all these different industries. And while you may be familiar, you may be more familiar with some of these jobs in the more conventional industries. Let me give you a couple of examples of jobs that you may not be as familiar with. And the first one is actually my own example. On the left, after I got my PhD at Penn State, I worked in the MEMS industry for a couple of years, Qualcomm MEMS Technologies, where we were developing MEMS reflective displays, flat panel displays, using a new technology, the MEMS technology, which as shown on this schematic, was based on tiny, tiny membranes, less than 1 micron thick, moving up and down. And so because that was a new technology, we had to, 30 more seconds, we had to basically identify potential failure modes and ways to prevent these failure modes. So that's required background in mechanics of materials, specifically at a small scale. And the other example I'm giving is a startup company, MedShape, co-founded by my colleague, Professor Ken Gall. And in that startup company, they developed shape-changing devices for orthopedic surgery based on shape memory materials. And I think it's a great example of where understanding the mechanical properties of materials, in that case, shape memory properties, really led to the creation of a successful startup company. So with that, I will stop, and I will be happy to answer questions at the end of the presentations. Thank you.